28 concepts, 7 layers. This is the ultimate mathematics iceberg. I made this iceberg myself, and it contains every single concept in math. From your usual 1 + 1 = 2 at the surface, to depression-causing equations at the very bottom, I will be covering it all. Let's start at the tip of the iceberg. Basic arithmetic is the math you learn in kindergarten. From buying groceries to even the most difficult calculus problems, it is used everywhere. Basic arithmetic includes addition, subtraction, multiplication, and division. Imagine you're at a market surrounded by fruits and vegetables. As you select apples, oranges, and bananas, you're performing addition, combining different quantities to find the total. Now suppose you've grabbed too many apples. No worries. By removing excess apples and ensuring you only buy the freshest apples, you are performing subtraction. But what if you want to share your fruits with friends? That's where multiplication comes into play. Let's say you have 3 friends, and each of them wants 4 apples. By multiplying 3 friends by 4 apples each, you will need 12 apples in total. Finally, division steps in when it's time to split the bill. Let's say the bill is $24, and you're splitting it equally among 4 friends. By dividing $24 by 4, each person has to pay $6. Overall, basic arithmetic lays the groundwork for more complex mathematical concepts, which will be deeper down the iceberg. We're now moving on to level 2 of the iceberg. This is where the infamous X, or any alphabet actually, is introduced. Elementary algebra builds upon basic arithmetic and introduces the use of variables and symbols to represent unknown quantities. There are 4 concepts at this level, which are linear equations, quadratic equations, exponents and radicals, and factoring. Imagine you're planning a road trip. You have a starting point and a destination. But what about everything in between? That's where linear equations come in handy. They're like the GPS of math, helping you find the path from point A to point B. Now, what if your journey isn't as straightforward? Maybe there's a mountain that you have to go around. This is where quadratic equations come in. They're like navigating a roller coaster, with ups, downs, and twists along the way. Think of shooting a basketball. Its path forms a quadratic curve as it goes up and then down through the net. But what about when you need to make something bigger or smaller? That's where exponents and radicals step in. Exponents help you instantly multiply a number by itself as many times as you want. And radicals? Well, they're like the reverse button, helping you undo all that multiplication. Last but not least, we have factoring. Factoring is breaking down a complex expression into a simpler one. Basically, factoring is the art of breaking down numbers into their building blocks. Think of factoring as untangling a knot, breaking down complex structures into manageable pieces. We're now moving on to level 3 of the iceberg. Intermediate algebra is basically the previous level, but more complex. There are 4 concepts at this level, which are systems of equations, inequalities, polynomials, and rational expressions. Imagine you're planning a party with friends, and you need to decide how many pizzas and sodas to order. This scenario represents a system of equations, where you balance the number of pizzas, x, and sodas, y, to satisfy everyone's appetite. By solving this system, you can make sure that each guest gets enough food. Now let's move on to inequalities, which is about boundaries and possibilities. Think of your personal budget. It's like an inequality that limits your spending while still being flexible. For example, if you have $100 to spend on entertainment each month, you can use inequalities to ensure you stay within your budget without sacrificing any fun. Next are polynomials, which are like the building blocks of math. From simple linear expressions to complex quadratic equations, polynomials can be used to describe everything, from the growth of populations to the trajectory of projectiles. For instance, when studying population growth, we use polynomial functions to model how populations change over time, which helps us understand trends and make predictions. Finally, let's explore rational expressions, which are basically the ratio of 2 polynomials. Think of planning a road trip with friends, where you need to divide expenses fairly. Rational expressions help us to divide the cost equally, ensuring everyone contributes their fair share without overspending. Similarly, in engineering and science, rational expressions are used in the design of bridges, circuits, and even chemical reactions. We're now moving on to level 4 of the iceberg. Geometry helps us design structures, navigate space, and understand the shapes and patterns that shape our physical environment. There are 4 concepts at this level, which are Euclidean geometry, trigonometry, coordinate geometry, and basic geometric proofs. At its core is Euclidean geometry, named after the ancient Greek mathematician Euclid, which explores the properties of points, lines, angles, and planes. For instance, when you measure the area of a rectangular garden to decide how much grass seed you need to buy, you're applying Euclidean geometry. Similarly, when architects design buildings or engineers lay out city streets, they rely on Euclidean principles to ensure structures are stable and proportionate. Trigonometry, another essential aspect of geometry, deals with the relationships between angles and the lengths of sides in triangles. It's incredibly useful in real-life scenarios like construction, astronomy, and navigation. For example, imagine you're tasked with measuring the height of a mountain. By using trigonometric functions like sine, cosine, and tangent, along with distance measurements and angle observations, you can calculate the mountain's height without having to physically climb it. Coordinate geometry, also known as analytical geometry, introduces the use of coordinates to represent points and equations to describe shapes, both 2D and 3D. Picture a team of engineers using coordinate geometry to design a suspension bridge, precisely calculating the positions of support structures and ensuring the bridge's stability and safety. Lastly, basic geometric proofs are important for logical reasoning in geometry, allowing mathematicians to establish the truth of math statements with logic. Think of it like a lawyer who presents evidence to support their case, trying to prove that their argument is the truth. We're now moving on to level 5 of the iceberg. Pre-calculus serves as a bridge between algebra and calculus. The 4 concepts at this level are functions and their graphs, logarithms and exponentials, conic sections, and sequences in series. Let's start with functions and their graphs, the backbone of pre-calculus. Imagine you're planning a road trip and need to calculate the distance traveled over time. This relationship between time and distance is a function, and its graph shows how your journey unfolds. From plotting the trajectory of a rocket to predicting stock market trends, functions and their graphs help us visualize and understand complex relationships in the real world. Next are logarithms and exponentials, which allow us to model growth and decay. For example, the spread of a virus over time. Its exponential growth can be described by an exponential function. On the other hand, the decay of radioactive elements follows a logarithmic pattern. Logarithms and exponentials help us to understand phenomena, ranging from population dynamics to radioactive dating, helping us understand change and transformation. As we venture further, we encounter conic sections, the curves and shapes that arise from slicing a cone. Think of the arc of a basketball shot or the elliptical orbit of a satellite around the Earth. These phenomena can be described by conic sections, which reveal the symmetry of nature. From parabolas in architecture to hyperbolas in astronomy, conic sections are everywhere around us. Finally, we have sequences and series, which are basically numbers that follow specific patterns and rules. Imagine a row of dominoes falling one after another, or the interest of a loan. These are examples of sequences and series, showcasing how mathematical concepts exist in our daily lives. Whether calculating compound interest or studying the Fibonacci sequence in nature, sequences and series help us understand patterns and predict future outcomes. We're now moving on to level 6 of the iceberg. Calculus is notoriously known for its insane difficulty, and it is the mathematics of motion and change. There are 4 main concepts in calculus, which are limits and continuity, differentiation, integration, and finally, how to apply calculus. Let's start with limits and continuity, which lay the groundwork for calculus. Limits describe the behavior of a function as it approaches a certain value, while continuity ensures that there are no sudden jumps or breaks in the function's graph. For instance, imagine tracking the speed of a car as it accelerates, where the limit represents the car's velocity as it approaches a specific moment. Next, differentiation allows us to understand how a function changes over time, giving us the rates of change and slopes. Think of differentiation as capturing the speed of a car at any given moment during its journey, which allows us to optimize performance in fields like engineering and biology. Integration, the reverse process of differentiation, allows us to find the total area under a curve. It enables us to solve problems related to accumulation, such as calculating total distance traveled, total revenue generated, or total mass accumulated. For example, integrating the velocity function of a moving object gives us the total displacement or distance covered at a specific moment, which is important for understanding motion and optimizing travel routes. The true power of calculus lies in how we apply these concepts to real-world problems. From modeling population growth to optimizing production processes, calculus allows us to make accurate predictions and informed decisions. For instance, calculus allows us to predict the spread of a disease, trajectory of a projectile, design efficient transportation networks, and even analyze financial markets. We're now moving on to level 7 of the iceberg. This level is kind of interchangeable with calculus, depending on the person. At this level, the 4 concepts are differential equations, linear algebra, abstract algebra, and number theory. Let's start with differential equations, which are like the engines of change in the math universe. Imagine you're tracking the temperature of a cup of coffee as it cools down over time. The rate at which the temperature changes depends on factors like the temperature of the room and the material of the cup. This relationship can be shown using differential equations, allowing us to predict how the temperature will change over time. From predicting the weather to designing spacecraft trajectories, differential equations are used everywhere. Next is linear algebra, the language of spaces and transformations. Picture yourself navigating through a virtual world in a video game. Every movement you make, every jump, every turn, is represented by a sequence of linear transformations. Linear algebra provides the tools to understand and manipulate these transformations, enabling game developers to create immersive environments and realistic simulations. But its reach extends far beyond gaming. Linear algebra is used to create technologies like image processing, data compression, and even internet search algorithms. For example, ChatGPT and the YouTube algorithm. Moving on to abstract algebra, we enter the realm of mathematical structures and symmetries. For instance, a Rubik's Cube, a seemingly simple but complex toy. Abstract algebra allows us to study the symmetries of the Rubik's Cube and understand its underlying structure. By exploring concepts like groups, rings, and fields, abstract algebra reveals connections between seemingly unrelated areas of mathematics. Finally, we arrive at number theory, which is all about integers and their properties. Imagine you're sending a secure message over the internet, protected by encryption algorithms which use prime numbers. Number theory provides the theoretical foundation for these cryptographic techniques, ensuring the security of our messages. But number theory is more than just cybersecurity. It touches on questions of pure curiosity, like the distribution of prime numbers and the nature of infinity. Thanks for watching. Please like and subscribe if you enjoyed the video.